Good afternoon, everybody, and welcome to the second live interaction of the course Mathematical Modeling of Manufacturing Processes. So I have searched that Google Doc file also. I think very few questions are there. Few clarification you have asked, as well as Google Doc form. We have that discussion forum also. I have checked maybe few cases you mentioned about specifically the assignment problem. But one thing I like to share with you that maybe some during this placing the assignment problem, maybe some mistakes may be there because it's mainly handled by the TA of this particular course. But that doesn't mean that the discussion of the theory will change. Not like that. Maybe you just stick with the whatever is given. That is the final in the PPT. So that discussion, and maybe you try to understand that before blindly looking into the application of the formula and solving this problem. Rather, it is more important to understand the problem, how it can be solved. Then any problem we can solve if you understand this problem, how this formula, all these things coming to the picture. So that is the one point. Second point is that when we'll be using some equation, we should look into the dimensionality of the equation. You put the dimension, check whether it is correct or not, or maybe some problem was a numerical problem is like that. Maybe units are different. Units are given different units. The values are given. So that's why before using that value in your even formula is there, you check the dimension of this equation. So then you'll be able to more efficiently the solve of the numerical problem. Specific to this, not only this course, any kind of this numerical problem will be able to solve. Now let us look into this problem that now we can discuss about this thing. So this course content, if you look into, there are 12 modules, and basically then all different modules, sorry, there are 11 modules but 12 week that we make this, so they cover most of the aspect of these things. And if you see the welding, casting, forming, powder metallurgy, even coating, additive manufacturing process, heat treatment process, even microscale manufacturing also, even that non-metallic material. So wide aspect of this has been covered in this particular course content. So it within this time frame, maybe only we are getting 30 hours of time to cover all these things. So therefore I covered the very basic elemental part, or very basic mathematical part, not maybe much details about the application or maybe that theoretical aspects that I have not covered in this particular course in detail. Maybe if you look interested in particular manufacturing process, maybe you can look into the individual course also, manufacturing process. But overall, we try to give some overall idea or maybe some mathematical aspect of the manufacturing process, and that is the objective of this course. So that even most of the time, so if you will get a lots of theory, but you may confuse that if you try to solve some problem, some design problem also, then this kind of numerical calculation may be useful, or some kind of analytical solution will help you to develop the understanding of this subject. So that's the purpose of this particular course. So we cannot don't expect that I'll be cover each and every part in details, and that is not possible actually within this time frame we have decided this course content. But maybe you can ask this question in particular topic, I can make some answer you with some reference or whatever you want to follow some things. That kind of information I can is possible to give. Now someone asked that things core topics of the course are not covered in the lecture, such as special casting techniques. Actually this is not the objective of this particular course. That's why I have not covered in the special casting topics. Rather, in general, we covered the what is the casting process and how we can look into the mathematical aspect of this casting process. That is the focus of this particular course. So that's why the all other theoretical courses, if you want to understand these different types of the casting process, their application and area, then maybe it is better to cover that particular the reference from this only casting processes. So itself, if you know there is a casting process itself, one very particular one is a course itself. So that you have to go in details about this particular course. Regarding the assignment questions, maybe some mistake is there, the putting the assignment question itself. But you mentioned that thing, the roll of the riser is used to feed molten to casting as it solidifies, and it is true also, and it is always true. That is the main purpose of this thing. And something missed, maybe some mistake is there in casting, that doesn't mean that it will change. No, that is not the reason for that. So it is true, but the correct answer is given. Maybe some mistake is there, we'll try to recover this mistake or maybe correct this mistake. But allow gases especially escape from the mold cavity. That is not the purpose of using, only the sole purpose of using the riser. Riser purpose is only to use to feed the molten material even at the last stage of the solidification, such that whatever shrinkage volume exists within this mold cavity during the casting process, that will be made up by the riser. That is the riser material. So that is the objective and purpose of using the riser. Explain the pattern of, you ask the pattern of the end sem questions and the some tips for the preparation of exam. So if we follow this assignment problem, so similar kind of the pattern will be there in the end semester exam. Maybe few questions exactly from theory and few questions from the mathematical calculation. But since it's a, this course is designed the mathematical modeling of manufacturing process, so we can expect more on the mathematical kind of questions. So that will be there in this particular course. And someone asked that shear angle formula if feed and spindle speed is given along with the depth of cut. You are asking the in metal cutting problem, but if feed and speed are given or maybe along with the depth of cut and chip thickness, is it the same formula that we use to find the chip thickness ratio with depth of cut and chip thickness and find the shear angle, or any other formula is there to find out it? So definitely see, we have derived the very basic chip thickness, what assuming some chip thickness and orthogonal cutting situation, we explain the two-dimensional figure and then we present that this is the chip thickness or this is the width of the chip. So from that value we have estimated the relation, the shear angle with other parameters. But if you look into the actual process, maybe I assume that maybe shaping, planing process or turning process, boring process, or maybe I can say the drilling process also, even milling process also. All the different types of process, the actual parameters are given, the depth of cut or maybe feed rate. So from feed rate and depth of cut, you have to understand from the how we can estimate from feed rate and depth of cut in terms of the chip thickness, uncut chip thickness, T1 value, basically uncut chip thickness or width of the chip, that can be linked with the actual process in terms of the feed and depth of cut. So there may be some, it depends on the actually, for example in turning process, the what is the principal cutting edge angle, that this uncut chip thickness and width of the chip depends on this principal cutting edge angle, and it relates with the feed rate and this thing, the actual process. So we have to simply convert it to the feed rate to in terms of the uncut chip thickness and width of the chip, and then use this formula to estimate the this chip thickness ratio or depth of this chip thickness ratio or the shear angle. That formula you can use it. That have to link with the problem. So that formula means the relation between the feed and maybe feed rate with the uncut chip thickness is different at the different processes. For example, in case of in drilling process or in turning process, this relation are different in this particular situation. So it depends on the principal cutting edge angle or the bit angle in case of drilling machine, in case of drilling process. So that's why you have to convert it in terms of the uncut chip thickness and these parameters. Now assignment problem, I think you have raised some questions, few assignment problem, maybe casting problem. There may be mostly the assignment problem. It's some mistake, calculation mistake may be there in this particular situation, particular cases, if it is not matching with the options. But always try to when you solve the assignment problem, is always try to follow the PPTs also. And maybe few cases some out of track questions may be there. It's not exactly 100%. You cannot expect that all assignment problem will exactly from the PPTs also. Some kind of deviation, some understanding is also required to solve the assignment problem. But very few cases we have given some problem which is little bit understanding is required of the actual PPT. So that kind of questions may be there, but that percentage may be very low. So this is always be there to design or to understand a particular course. You have to understand this particular courses or particular topics. Then you will be able to solve some out of track problem also. So it is quite obvious out of track problem may be there, and even in final exam as well. Someone asked to good reference book associated with the welding process. Maybe you can look into this different uh, welding processes, that physics of welding, the principle of welding process. If you see, I have listed lots of few books, welding metallurgy, also computational welding mechanics. So if you are very interested to looking into in details about the welding processes or associated with the numerical problem, you have to understand the physics, that means how it is happening. Then the knowledge of the heat transfer may be required to solve certain problem. And then few cases, all the cases, most of the cases we have explained also. But suppose you want to understand the temperature distribution, then you can follow some kind of analytical solution of the temperature distribution in case of the welding. So all this kind of welding, very clearly you understand these things, then there are several books. You can follow any of the books. For example, if you want to follow some friction stir related welding process, so there is one reference book I have mentioned already, Advances in Friction Stir Welding and Processing. They published by Elsevier. So there you can follow in details about the calculation of the friction stir welding process. Now someone asks, maybe you have mainly the cutting, metal cutting process and casting process having some understanding difficulties in understanding. Maybe you can look into this little bit, just revise this part to understand this thing. So first thing is the metal cutting process. If you want to relate the different parameters, we assume the orthogonal machining process. Orthogonal machining process, because it is easy to understand this relation between this process and its merchant assumptions for the two-dimensional orthogonal cutting. Basically, we are assuming the two-dimensional orthogonal cutting operation. Here you can see this depth of cut, this thing, and the primary zone, secondary shear zone, all are important, and maybe depth of cut, or maybe you can say the uncut chip thickness is the same in this aspect. And then chip velocity is VC, which is different from the tool velocity, and the primary shear zone. Basically, primary shearing happen one particular plane. We assume that, but it actually happens over a particular area, finite area. But for simplicity in calculation, we assume it's happening over a plane, over a particular plane, and that shear plane, primary shear zone, that particular plane makes an angle, that is the shear angle. So with this all configuration, we can do the calculation in this thing. You can see here that the shear angle is very defined, phi, and the chip flowing is there, and the rake angle also there in the tool. Rake angle is well defined, the alpha rake angle. These are the main things: shear angle, rake angle, and then we are relating, and the other is the friction angle. Basically, the friction angle depending upon these two normal forces and the friction forces making this thing. Some angles are there. Then we are making the force balance during the actual machining process. So there is a continuous machining process is happening. So we can take a picture at a particular instant. Then you will feel that it's a balance with all the forces, force components. From this balance of these force components, and the different velocity components are there, different force balance also there. From there we can do the different calculation, and that it's a better represented by the force diagram, the merchant force diagram. So that means all force components, they are representing one particular circle, and the resultant force is the representation of the diameter of this circle. So we can use some geometric principle here also, and then we can relate the different forces. So simply represent the different forces here within this circle, which is the resultant force. And if you take the free body diagram, say from tool side, free body diagram, or the workpiece side, then representing this thing. So that's why one represent R, and other cases we are representing the R dot. So that resultant force from the tool side and resultant force from the workpiece side remains the same, but they act in opposite direction. So here we can see accordingly shear angle we define here, the shear angle, and then rake angle also define, the friction angle. Basically these three different angle we can define, and then different force components we can derive also. So frictional force between the chip and tool will be there. So that is the FF represent the frictional force, and the normal force is that accordingly FNT represents the normal force. Similarly, the shear force. Shear force means the shear force acting on the shear plane, which plane the shearing happens, Fs. And then corresponding angle, shear angle is also given. And the cutting force, we represent this Fc and Ft. There are two components. Fc is the cutting force we define in such a way that which direction the tool is moving. So along the direction of the linear velocity of the tool, one particular direction, and at the same direction we represent the cutting force. So when we estimate the power requirement, then we know the force into velocity represents the power. So then cutting force into velocity represents the power. That we are getting this relation. Now different plane we are making the force balance, and then we reach all this kind of the conclusion. If you very carefully look into this already provided to you, the relation between the different forces, then we'll be able to reach all this kind of the relation from this force diagram. Similarly, then you relate this is the other part of this cutting problem, that is the shear angle. So then this will be shear angle, relate the chip thickness values of the different chip thickness or chip thickness ratio. Here you can see T by TC. T is the uncut chip thickness and TC is the after deformation, then what is the thickness of the chip, that is the representation of the TC. So it's not necessary T and TC should be the same. T and TC should be different, because heat generation there some expansion may happen because it's a deformation process. So therefore T and TC, this T and TC ratio is called the chip thickness ratio. So it is very easy to find out in this thing. First to define the different angles, the shear angle, which one the shear angle, rake angle, and the accordingly the other this here the relates the shear angle and the rake angle. And so shear angle and rake angle we define this from the geometry. Here you can see, and then chip thickness you measure the which is normal to the this tool face. The direction perpendicular to the tool face along this is the along this direction we measure the chip thickness, not in the other position. So then make the maintain the volume conservation. That means before cutting and after cutting the volume should be the same. For example, simply LW into T. L is the length, for example, and length of the chip. W is the width of the chip before cutting, and T is the uncut chip thickness. That means its thickness before cutting, so that we are supposed to cut. And after cutting, then you are getting the chip thickness is the LC, thickness is TC, the width WC, and length LC. Make this equal, because volume conservation will always be there. So before cutting and after cutting, the total volume remains the same. Now from here, we assuming the orthogonal cutting, normally the width of the same before cutting and after cutting same, and the L into T equal to LC into TC. That means length into time, that times, and LC into TC. Then TC means the chip thickness. Sorry, not time, here is the this thing. This is the thickness, before thickness. So L into T, length into T, that before and after LC into TC remains the same. So therefore from here we can say T by TC equal to LC by L. That means either TC by T, that if the values are available, then that represents as a chip thickness ratio, or if we measure the L before, what is the length of the chip we are supposed to cut, and after cutting what is the length of the chip. So that we can measure it, then we will be able to know what is the chip thickness ratio. Now length of the shear plane AB, the length of the LS can be expressed like that, LS T by sin phi from this relation alpha rake angle. So RC, chip thickness or ratio of T by TC, can be represented in terms of the angle phi and alpha. That is already given, and from there we can represent the shear angle phi equal to tan inverse this. So basically what we represent this way, because chip thickness ratio is easy to measure, because experimentally we can measure the after chip formation, we can measure the chip thickness, and before cutting also we can measure it, T. So that represents the RC, and cos alpha rake angle of a tool is well defined, RC alpha, and from this value we can estimate what may be the shear angle in the particular situation. So this shear angle depends on this, what is the chip thickness ratio as well as the rake angle. So it can vary also, but if there is a chip thickness ratio or different rake angle, tool rake angle are different, then shear angle can vary. So from here shear plane we can define all these things. Normal shear plane we can estimate what is at the normal. So shear stress, you have to define the normal shear stress and normal stress. Shear stress must acting the parallel to the plane. Shear stress is acting in this particular direction, but normal stress is acting the normal to this particular plane. So that's why we can differentiate which one is the shear stress, which one is the normal stress. That calculation is already given. Now velocity component also. From here velocity components, we can see the different component of the velocity. The chip velocity, one is the tool velocity, what velocity tool is moving. Other is the shear plane velocity, so that is the Vs. So making Vs, Vc and V. So then we use this relation, velocity relation between this. We make the velocity triangle with a closed triangle. And if you understand the first year engineering mechanics course also, this if we making the closed triangle, and let's use this define all the different angles, which one is phi, which one is alpha, all these three angles. Then we can simply use the velocity relation, Vc by sine phi, V by cos phi minus alpha, and Vs by sine 90 minus. So from the relation we can relate the different velocity components. But finally, Vc by V is equivalent to Rc. I mean chip velocity by V. When cutting tool velocity and chip velocity, that ratio is equivalent to the chip thickness ratio. So that way we can say that we can get this kind of the relation. And similarly, that is also important. The shear strength, how to estimate the shear strength. Simply we have to understand the shear strength means basically take an element that we have given, also take an element, shearing happened parallel to this plane particular, the shear stress is acting, the deformation, small deformation delta s, and the thickness over the distance delta y. So same analogy you can apply in this particular machining process also, that we have clearly given here, that which one will be delta s, which one will be delta y. From there you can see there are two components of the shear strain estimate, that consists of cot phi plus tan phi minus alpha, and that is the shear strain. And they can simply verify also that can be represented in terms of the Vs by V, and that relation is there, because just previous slide we have shown the chip thickness ratio and the different velocity components ratio, we find the relation. So from there we can say the other relation also. So these are the shear strain calculation. Now strain rate basically the strain rate, simply understand the d epsilon by dt, that means change of the strain with respect to the change of the time. So it simply said delta s by delta y is the strain, and divided by delta t is the time. So strain divided by delta t, that indicates the strain rate. So now delta s by delta is simply delta s by s equal to v into t, velocity into time. So therefore delta s by delta t represent the velocity. That means the velocity means along the shear velocity, along the shear plane, what is the velocity, or maybe we can the shear plane velocity. So that represents the vs. So vs by delta y has been defined the perpendicular to this along the normal to the velocity vector. So therefore delta t time is the time interval to achieve the shear strain. This delta t can be very small also. So from here we can estimate the Vs value, put the Vs value, and delta y, depending upon the delta y value, thickness you are considering, we can estimate what is the value of the shear strain rate. Now this shear angle and the friction angle, we try to estimate the relation between the shear angle and the friction angle, such that during the process the requirement force and energy requirement will be minimum. Looking into that principle, what will be the minimum energy required to achieve these things, we are relating the different velocity components, and basically we estimate the power requirement, because power equal to that or energy requirement, Fc into force into velocity. So Fc can be estimated in the form of the different angle, shear angle and the maybe tool rake angle, or in terms of the friction angle also, and velocity v. So once we do this, we minimize this problem, then we will reach some relation between the shear angle, friction angle, and rake angle. So that phi equal to that pi by 4 minus beta by 2 plus alpha by 2. So from this relation, this is the relation, but this relation is varied if you want to the condition for the achievement of the minimum energy required during the machining process. Then only you can relate, you can use this relationship. But maybe this is very ideal situation, because lots of assumptions are there. For example, that shear stress and normal stress of the tool force not varies uniformly. There may be distribution not uniformly varying, maybe, or friction angle also varies along with the contact length. So if you took the realistic thing and it is different, and then you have to consider the other aspects also, then we can be some other relation. Okay, so I think that is already explained. I think same principle if you want to minimize the power requirement, but you assume the other cases also, that which is deviates from the Marcham's assumptions, that different expression of the normal stress component. That means if you use the shear stress also depends on the normal stress components, then you reach some other expression. That is the second one. Now some part of the solidification also we can tell something, that this solidification, coming to the solidification, because maybe you know that solidification time depends on the volume by area square or some other formula you are using, but in this particular uh, um, this cases we have explained that different solidification processes, that how what we can estimate the solidification time based on the heat transfer mechanism actually by looking into all the heat transfer mechanism. But you have to relate the what is the practical problem, then what type of mold casting you are following. Accordingly, you have to use the principle of the heat transfer mechanism. And in this case, maybe rate of the solidification, for example, in a thin layer. In this case, I think there is a resistance occurs in the at the mold wall. So maybe very uh, in this case maybe very big casting process or sand mold casting with a particular thickness is there, then we assume certain heat transfer mechanism. First you have to understand the mechanism of the heat transfer to the actual casting process, then you pick up this particular analysis. Okay, so first solidification time, we estimated the rate of the solidification is basically K into V by A, that volume by area ratio square. So there, that because it's a volume by area, because volume means in the casting process the heat content, we normally understand the heat content within this particular component, and then or geometric volume, and then area represents that is responsible for the loss of heat by convection and radiation from the surface. So therefore both are important parameter which relate, which decide the this thing, that solidification time in this particular case. So that this case solidification factor is depends on the all the material properties of the mold material as well as the cast material. So from that point of view we can estimate the solidification factor and then we estimate the solidification time. But this formula is mainly applicable in case of the sand casting process, and maybe you in that cases you are making very large casting, that cases we use this formula. Here we have shown that two components, we have already explained this thing, the rate of the solidification. I hope just simply application of this formula, nothing else. Similarly, the same formula you can use this on the different problem. In this case, solidification time for complex contours. For example, previous cases we assume that the solidification happenings and that all this heat transfer as in assuming a plane wall, in this case. But if there is a mold and cast material, the mold solid liquid interface, maybe mold and cast interface, it is not very straight. In the practical cases, it may be a convex type of surface may be there, or concave type of surface is there. So that means if it is not flat surface, if it is either concave or convex type of surface, then it affects the heat transfer, rate of the heat transfer. So that means it modifies the rate of the heat transfer equation. In that case, we need to consider the, if you want to consider this curvature effect, then we have to treat the solidification problem in different way. That we have already explained. We use some non-dimensional parameter and we relate, we find out what is the value of this non-dimensional parameter to solve it. Then we can find out the what is the solidification time. And we have explained very clearly when taking the particular example also. That's not necessary to explain once again. Okay. So other cases, the solidification is the predominant interface resistance. Predominant thermal resistance in the mold metal interface. So this process includes permanent mold casting and die casting. For example, in case of the permanent mold casting and die casting, the heat transfer is little bit different when you analyzing the solidification time also as compared to the sand casting. So in these cases, the solidified metal actually induce the resistance to the heat flow. So in that case, if we analyze these things, then we can reach some other expression. So here if you see the solidification time only depends on the V by A ratio, not the V by A square. So it means that what type of casting process you are handling, accordingly you should use the what is the equation for the solidification. So for example, two different cases we can use a different solidification time, that it depends on the different parameters. So that has to be understood in this particular situation. Now somebody asks the riser design and placement. Actually riser is very important in this in casting problem, and very simple reason of using that riser is that it actually fed the molten material. So in principle, riser should solidify after the solidification of the cast volume. And second thing is that the volumes of the riser should be as minimum as possible, because simply it is the wastage of the material or wastage of the energy also. So if you unnecessarily keep the large volume of the casting, then you have to melt that you have to fill that cavity with the mold material. So I think it's some energy involved in this cases. So minimum volume possible we can keep, because it should not, it is finally not the part of the actual cast product. So therefore that has to be removed. So therefore minimum volume, at the same time the riser should solidify after solidification of the cast volume. Looking into these two conditions, normally we design the riser. But in this case we are focusing only on the very simple, without looking on the what may be the position of the riser. Position means whether we should use very large casting in the multiple riser, or the location of the riser. That is the different thing, or that is the, in that cases maybe in depth in analysis is required. But we are not, we are looking into very basic. We are assuming this thing that the only single riser we are using during the casting process, and little bit about placement in the different aspect, a very simple aspect that we can discuss. So that is also important. The solidification time mainly depends on the volume by area ratio or A by volume ratio. So minimum A by volume ratio will be desirable when you try to design a riser in case of the casting process. Here you can see that we are discussing only two types of the riser. One is the top cylindrical riser, another is the bottom cylindrical riser. Top cylindrical riser is that the riser is placed on the top of the mold surface. So therefore material can be feeding from the riser to the mold material at the last stage of the solidification. So that if you see that it is important that we are talking about the volume by area ratio. So therefore the actual area for responsible for the losing of the heat in this, in case of riser, in this cases the top cylindrical riser, it's not all the surface is responsible. That along the periphery, that means we use that surface area, that is very important in riser design. If you use the top cylindrical riser, then accordingly you have to consider the surface area which is responsible for the losing of the heat. So in this case we have considered the surface area pi dh plus pi by 4 into d square. Only the top surface area we have considered, not the bottom surface, because bottom surface is in contact with the mold. So that surface is not exactly effective for the losing of the heat from the surface. So that's why we consider this different area, and we minimize this thing. We can do some relation between the H and D, that in general that you can call as a design of the riser. Similarly, side cylindrical riser. Side cylindrical riser, if you look into it, is placed the side of the mold cavity such that all surface area is responsible for the losing of the heat. So when you're accounting the surface area, then you should consider all the surface area. So A is pi dh plus, here you can see 2 into pi by 4 into d square. That means we are considering both the top surface and the bottom surface, both we are considering. And then the calculation changes little bit also. Then in this case the design says that H equal to D. So this kind of relation we can reach, which is different from the uh, top riser. To top riser and side cylindrical riser, these are the two different aspects, and depending upon the surface area is responsible for the losing of heat, we can decide the design of this particular riser. So I think that's all this discussion on these things. Now you have any questions, the quickly you can place your questions in the chat box. So if there is no question, maybe I can stop here. Or fine, I should wait for a few minutes. Okay, thank you. Thank you very much for your kind attention.